Hello, and welcome to this short video on smooth analysis of order types. My name is Till or Tillman. My last name is Milzo. This is joint work with Martin van Schreik and Ivor van der Hoog. Okay, so let me start with the definition of order types. So here we have given a set of points A, B, C, and D. And an order type tells us for each triple whether this triple is oriented clockwise, counterclockwise, or it's collinear. So let's start with the triple A, C, B. We see that this triple lies on one line, so it's collinear, so the order type assigns it the value 0. The triple A, C, D is oriented ACD in clockwise direction, so this is mathematically negative, so the order type assigns it the value -1, and for the triple B, C, D, here always in alphabetical order, they're oriented counterclockwise, so mathematically positive, so we assign it the value plus. So that's the order type. Point set, it just tells us for each triple positive, negative, oriented positively, negatively, or collinear. So that's a very simple combinatorial information of the point set. Okay, so now you may wonder, if you've never heard of order types before, why should I care about order types? It's a very valid question. So let's say you have given a set of points and you want to compute something. Let's say the onion layers of that point set. Well, then all you need is the order type. Let's say you want to compute a triangulation, all you need is the order type. You want to count triangulations, all you need is the order type. You want to find a cactus, the cactus layers of the triangulations, and all you need again is the order type. You want to find what's called a pizza cut, where half the point is on the top, half the point on the bottom. You need all you need is the order type, all the combinatorial information, right? So if I know whether these 3 points are oriented clockwise or counterclockwise, so I know whether this point is above or below that line. Let's say I want to find a ham sandwich cut. Again, all you need is the order type. Okay, so the order type is like the combinatorial information of the order type are enough to recover all of this information. So that's nice. So why do we care specifically about the order type? Wouldn't it be like too complicated way of doing things? Maybe, but so let's look at this set of points, right? So try to figure out whether this is oriented clockwise or counterclockwise. It's pretty tough, right? So a computer has to do this all the time implicitly. So if it wants to compute a triangulation here, it needs to know whether it can, on which side this point lies of the line between those 2 points. So it's kind of guessing, and it may maybe one time say -1, the other type +1, and that can lead to errors. So in order to avoid these errors, the computer needs to store many bits. So this is even happening in practice. So there's this computational geometry algorithms library called Seagull, and they have many of the algorithms or important algorithms are implemented there. And what they do in order to avoid these inconsistencies, they compute all the points precisely. So they have this precise computation methodology, and that makes it fairly slow. They do this because they need to avoid these errors, which occur if the order type is sometimes or is inconsistently stored. Okay, so in this talk, this is a theory talk, and we wonder, so how many bits, how many 0 ones do we have to store to save the order type correctly, to compute the order type always correctly? And the answer, theoretically speaking, is quite bad. So we may need to store an exponential number of bits. So if you have n points, so for each point, like you need exponential number of bits, which is very bad if you want to do computations. So that's a theoretical worst case result. So this is upper and lower bound. And what people recently did was they looked at random point sets in the unit square. And so they looked at the expected number of bits, and the situation is much, much better. So they need 4n log n bits for all the points together, for n points. So that is 4 log n bits per point, which is very good. It's double exponentially better per point. Okay, so let me summarize. So if we look at the number of bits that we need, so then theoretically we know exponential number of bits may be necessary, and we have examples for that where this is indeed the case. And then for random points, we are in a happy situation that we only need logarithmically many number of bits. And so this talk is about what happens in between. So of course, points at the practice, they are not really random, but they may all not be as bad as these worst case point sets. Okay, so what I explain you now is that we know what order types is and what it's used for. So we study, I give you a short overview of smooth analysis. So this is now smooth analysis in a nutshell. Okay, so let's start with looking back at worst case and average case. So here we have this graph where on the x-axis we have maybe all the instances of some algorithmic problem, and on the y-axis we may have the running time for each instance. So for instance here we need a very large running time, but for and that may be the worst case. So that would be the worst case. But usually the running time that you observe is that one in practice, because you may never encounter that particular instance. So worst case analysis can be too harsh for what you want to do. Okay, so now let's look at average case analysis. Here we have another graph, and again on the x-axis are all the different instances, and on the y-axis is the running time for those instances. And then the average says this is the running time, because all those instances here, there are many of them, and they're dominating the analysis, the theoretical analysis, but maybe the type of instance you encounter in practice, they're kind of structured, they're not looking completely random, and they may be actually worse than what is done in what the theoretical analysis says. So worst case analysis is a little bit too pessimistic sometimes. It's often surprisingly realistic actually. And average case analysis is often considered as too optimistic. And so if you look at the literature, worst case analysis is really dominating the literature for algorithmic problems. It's maybe also a little bit easier to understand and to analyze. Okay, so now we had to look at those two things, and smooth analysis tries to smoothly interpolate between those two types of analysis. Okay, so the underlying idea is you may have in your problem instances a lot of structure, which happens, actually just is there, but there's also a certain amount of randomness. Okay, so how does it look like for a particular instance? So you see this instance here, right? It's a polygon. It's a layout of let's say a building, and then the layout has some structure. Like there are different rooms. Let's say this is a room, and there's like a purpose of this room. Some thought about having these different rooms, but what is the exact width, for instance? It's maybe kind of random. Right? Maybe a random choice that was being made. It could have been a little bit smaller, a little bit bigger. Yeah, so that may be a random part of that instance. Okay, so let's go to a more mathematical definition. We stick with polygons. So what we want to do is we want to look at the max overall instances. So we take the worst instance we can. then perturb it a little bit and integrate over all these perturbations, and then look at the running time for integrating the costs of all of those perturbed instances. So the cost can be measured, is often measured in running time. Sometimes also space is considered. We are considering here the number of bits that are needed for that particular instance. And yeah, so let me point out here, so if we add no randomness, right, so we don't perturb at all, then we're integrating over exactly one instance, and that would just be the worst case. So it doesn't really, this integral can be deleted, essentially. So if we add no randomness, we're in the worst case. If we add a lot of randomness, we're in this happy case, in the like average case analysis. So to see this, consider here we take the max, we need some really bad instance, but we perturb it so much that we can't really see what instance we started from. If the perturbation is strong enough, then what instance we started with is essentially irrelevant. So that's why the more randomness we add, the more we tend to be in this average case scenario. Okay, so smooth analysis was recently, or well, historically, relatively recently in 2001, invented by Spielmann and Teng, and essentially, yeah, they used it to analyze the simplex algorithm, and they received the Kurt Gödel Prize for it, which is one of the biggest mathematical honors you can receive for a single paper, and they received it because they introduced this concept and they analyzed the simplex algorithm. And the prize is so important because while smooth analysis is such an involved concept, this prize shows that the community thinks this is a good concept and we should work with it. So it's an accepted model of analyzing algorithms. So I think it's very important to have that prize. Okay, so how do we apply smooth analysis in our case? So the worst instance we start from are, in our case, like point configurations. And then we add some randomness to it. So we have some, for each point, we have a disk of radius delta around it, and we perturb the worst point to a new point, which we mark in blue here. And then we want to make some statement about we get a new order type in that way, and we want to make a statement about the bit complexity of that new point. And in order to do that, we snap it to a grid. And when we snap it to a grid, then we know how fine that grid is, and because we know how fine that grid is, we know how many bits we need to store this point. And then hopefully here these new points will have the same order type as the blue points. Yeah. Okay, so let me try to re-explain this again. Okay. So we start with some order type. This is our input. So we start with the worst possible order type. And what we do then is we get a point set representing that order type. So if it's a representable order type, there must be a point set which represents it. And we only care for order types which are representable. Then we add some randomness and we get a new point set. So from that representation, we get a new point set by adding this randomness. And then the new point has a new order type. And from that new order type, we want to know its bit complexity. And this is a process that we're doing. Okay, so let me re-explain this because I think it's really confusing. So you can think of it, we maximize over all point set in the unit square, we integrate over all options to perturb it, and then we look at the bit complexity of the new order type, which comes from this blue perturbed point set. Okay, so let me carry some points home here, which I think is fairly confusing. So we have an algorithm, right? What is an algorithm? An algorithm takes some input, does something and gets some output. Here, this algorithm takes an apple, takes an orange squeezer, and then gets some apple juice. The algorithm may not always run correctly, but assume it works, okay? Then smooth analysis, traditionally applied, is to the apple. We apply the perturbation, the randomness we added to the input. Here we do something differently. We add the randomness to the output. So our output would be, we've given an order type and we get a point set. And we add the randomness to the point set, not to the order type. But then from that perturbed point set, we get a new order type indirectly. So like our model integrates over perturbing the output, and that gives us some random distribution on the input indirectly. Okay, so I hope that was clear. So what is our result? So if we look at the expected number of bits, then we will have 4n log n divided by delta. So this is kind of the best we could hope for. So if delta equals 1, then this is just the random case that we had before. And if delta would be 0, then okay, that would be infinity. But yeah, so we are very we are very fragile. If we perturb just by a teeny tiny bit, then the number of bits is very limited. So yeah, the bad instances are very fragile to small perturbations. This is kind of what you would expect. Okay, so let me tell you some of the key ideas of the proof. The proof is actually maybe simpler than the conceptual steps that led to it. So again, we are in a scenario where we have these worst case red points. So we just start with any set of red points here. Then we perturb it by delta, we perturb it within a disk of radius delta, and then we snap it. The snap point may lie even outside of those disks in some cases. And so what we need to preserve when we snap is, so we have here this point that, let's say it's oriented positively. If we snap it, we really need that it's still oriented in the same way as before. We don't want this to change because we don't want the order type of the snapped and the non-snapped to be changed because we want to say something about the order type of the blue points. In contrast, so we have here these red points, we perturb them, and as you see right here, the red point is below the line, here the blue point is above, so the order type changed. But we don't really care because we are allowed to change the order type of the worst case point set, right? If we would never change the order type, then we would not have a distribution on the order type. We would have a distribution which just always has the same order type. So that's okay. Changing that order type is okay. Changing the order type as a perturbation, that is kind of what we're looking for. Changing the order type as a snapping, that's not what we want. Okay, that's the important bit. So now let's see, if we have 3 points here, and there's a point, the middle point is very close to the line of the 3 points next to it, then it can easily happen that when we snap that point to the grid, it changes the order type. And this is bad, this is what we want to avoid. And so what happens is we get this lemma that if we have a fine grid width W, and every point is at least root of 2 times W away from the line of the defined by the other two, then the snapping will be fine. And so the proof idea is very simple. It's a little bit tricky to do the details, but so no one is snapped by more than W divided by root of 2 because, well, you're always within that distance to one of the grid points. And then if you want to go as much as possible in the wrong direction, well, you cannot, because you see it's just not enough. You're just too far away, as you can see in the picture. Okay, so that's the key lemma and the key observation that we made. And then, so we use it. So let's say we have here this one point, and then this is a bad region of that point. So if these are two other points which are already perturbed, then the third point, if it lies in this red region after snapping, may get changed, which would be bad. So and what's the size of this region? So it's roughly W times delta. We note that this bad region here is of width roughly W, with W is the grid width, and delta is the radius of the disk. So here I omit some constants. So now if we want to know the expected value of all the points, we can use linearity of expectation. So we just need to know the number of bits for each point. Okay, so let's look at the probability that the point gets changed. So it is in a quadratic number of these triangles, and that's denoted by AT, the probability it's like in one of those bad regions. So then we want to look at the event that it's in one of those bad regions. And for that we can use a union bound to upper bound this. And so we just sum over all of them instead of taking the union. And then how many of these triples are there? Well, there are only quadratically many pairs of other points. W times delta denotes the bad region. Delta squared is the whole region that it could fall into. So this can be kind of simplified to W times n squared divided by delta. So this would be the probability of a bad event happening. So if we choose W like the reciprocal of that value, then with appropriate constants, then the probability gets very small that a bad event will happen. And well, if the probability is very small that a bad event will happen, then okay, then the expected value is no bad event will happen. And it's not always true, but in our case it will be. So the expected number of bits is 2 times log of 1 over W, right? So the finer the grid is, the more bits I need, and I need logarithmically many because the width can be expressed with bits. So we take a logarithm, and we have 2 because for the x and y coordinate. Okay, and yeah, that was a little bit technical, I know, but I just want to show you that like these calculations, they're pretty straightforward, and we use really simple things like union bound and linearity of expectation. Okay, thanks, and hope you enjoyed the talk. Don't give up.